Now that we've reviewed some vocabulary with power series and we know how to take derivatives of power series, we know how to treat them as functions, we know how to combine them, we know how to change indices, all of these things, now we're ready to solve some differential equations with them. So today we're going to be talking about solutions about ordinary points. You might not know what an ordinary point is yet, but that's part of what you'll learn today. So let's get into it. The first thing we need to do to talk about solutions to differential equations about ordinary points is to know what an ordinary point even is. So a point x equals x sub 0 or x naught is said to be an ordinary point of the differential equation a sub 2 of x times the second derivative of y with respect to x plus a sub 1 of x times the first derivative of y with respect to x plus a sub 0 of x times y equals 0. If both coefficients p of x and q of x in the standard form, the second derivative of y with respect to x plus p of x times the first derivative of y of x plus q of x times y equals 0 are analytic at x naught. So remember, we get from our differential equation with our a of x coefficients to our standard form by dividing all of our coefficients by a sub 2 of x. So p of x is going to be a sub 1 of x divided by a sub 2 of x, while q of x is going to be a sub 0 of x divided by a sub 2 of x. So we need p of x and q of x to be analytic at x naught. Remember that to be analytic at a point means that we can represent the function p of x or q of x as a power series that has some positive or infinite radius of convergence. Now, it might be difficult to decide which functions fit that definition or not. Another definition that is perhaps easier to wrap our minds around is that a function is analytic at a point if it is infinitely differentiable. That means we can take the first derivative, the second derivative, the third derivative, the 20th derivative, the 1000th derivative, and so on. So some functions that you might think of right off the top of your head that we could differentiate over and over again, perhaps e to the x, that when we differentiate it, we get e to the x, and that'll continue to be the case no matter how many derivatives we take. Or sine of x becomes cosine of x, and then becomes negative sine of x, which becomes negative cosine of x, which becomes sine of x, and so on. Or even a polynomial, where once we take enough derivatives, we're taking the derivative of 0. Taking the derivative of 0, 0 is differentiable, even though its derivative is 0 always. So those are some common analytic functions at the point x naught for our p of x and q of x. Now, really quick, also, a point that's not an ordinary point of the differential equation is said to be a singular point of the differential equation. So we want to make that distinction. Today we're going to be talking about ordinary points, though. So let's take a look at a couple of examples. My first example in green, the second derivative of y plus e to the x times the first derivative of y plus sine of x times y equals 0. To determine if my function is analytic at a point, so we're taking e to the x and saying, well, is it analytic? And we have some point that we want it to be analytic at. So let's just figure out what values can it take? What values can it be analytic at? So what values of x can we plug in that if we're taking derivatives over and over again, we want the function to continue to be defined. So e to the x, we can take the derivative over and over again, and it's defined for any value of x that we put in it. Similarly, sine of x, we can take derivatives over and over again, and no matter what value of x we put in, it's defined. So for this differential equation, all values of x in the real numbers are going to be ordinary points of the differential equation. Taking a look at my second example in pink, we have x squared minus 1 as our coefficient on our second derivative. So we need to put it into standard form, this differential equation, before we can talk about whether it's analytic or not, the functions p of x and q of x, because we don't know what those are. To find those, we're going to be dividing by a sub 2 of x, so we're going to be dividing by x squared minus 1. Take a look at the coefficients that are currently on the first derivative of y and y. Notice that one of them is 2x and the other one is 6. These are both infinitely differentiable. And when we divide by a sub 2 of x, we're dividing by a polynomial, so with the quotient rule, we could take the derivative always. But there's going to be a value of x where this is not defined. Namely, any value of x that's going to make my denominator 0 in my p of x and q of x quotients that I end up with is going to end up with an undefined function at that value of x, and consequently it can't be an ordinary point. So I need to find out when a sub 2 of x equals 0. That's when those values of x are going to be the points that are not ordinary points for the differential equation. So x squared minus 1 is going to be 0 when x is plus or minus 1. So plus or minus 1 are not ordinary points. However, anything else is an ordinary point of this differential equation. Plus and minus 1 in this case are singular points. So now that we can determine when a point is ordinary or not, we can talk about the existence of power series solutions. So if x equals x naught is an ordinary point of the differential equation a sub 2 of x times the second derivative of y with respect to x plus a sub 1 of x times the first derivative of y with respect to x plus a sub 0 of x times y equals 0. So x naught is an ordinary point of that differential equation. We can always find two linearly independent solutions in the form of a power series centered at x naught. That is, our power series solutions would look like y equals the sum from n equals 0 to infinity of c sub n times the quantity x minus x naught raised to the nth power. A power series solution converges at least on some interval defined by the absolute value of x minus x naught is less than r, where r is the distance from x naught to the closest singular point. R is our radius of convergence in this case for this power series. Now a couple of notes about this theorem. Y equals the sum from n equals 0 to infinity of c sub n times the quantity x minus x naught to the n is a solution about the ordinary point x naught. And r is the minimum value, or lower bound, for the radius of convergence of that power series solution. So let's take a look at an example. Let's say I have x squared minus 2x plus 5, that quantity, times the second derivative of y with respect to x, plus x times the first derivative of y with respect to x, minus y equals 0. And let's say I want to find the minimum radius of convergence for a power series solution. And let's say my ordinary point that I'm finding this about is x equals 0. So I need to find the values of x that are singular points for this differential equation. Again, noticing the coefficients on the y prime and the y term, I know that all I need to do is find out when the coefficient on the y double prime is going to be equal to 0. So I'm going to set that equal to 0 and solve for x. So we have x squared minus 2x plus 5 equals 0. This doesn't look like something I can easily factor, and so I'm going to use the quadratic formula. So I'll have x equals negative b, so 2, plus or minus the square root of negative 2 squared minus 4 times 1 times 5, all divided by 2 times 1. So if I simplify that, then I find myself with 2 plus or minus the square root of negative 16 divided by 2. It's completely okay to have singular points that are imaginary numbers. So I can actually take the square root of negative 16 and get 4i from that. And dividing by 2, I get 1 plus or minus 2i. So those are my singular values, my singular points. So now that I know the two singular points, I can find the distance from 0 to them in the complex plane. So finding that distance, I'm going to be taking the square root of 0 minus 1 squared plus 0 minus 2 squared. That's the distance formula and looking at the complex plane to figure out that that's what I need to do. And when I do that, I'm going to end up with the square root of 5. So we know that these singular points that we've identified are a distance of square root of 5 from 0, which was the ordinary point that we were trying to find a radius for. So that means that we know that the radius is going to have a minimum, the radius of convergence will have a minimum value of square root of 5. Notice we didn't have to solve the differential equation to know the radius of convergence of our solution. So you can be asked about the minimum radius of convergence for solution functions and not need to find those solution functions to identify what that radius would be. The final thing we're going to talk about is finding a power series solution to a differential equation. Rather than talk through a bunch of theoretical steps, we're going to work through an example and talk about the steps as we go. The example that we're going to work with is the second derivative of y with respect to x minus x times y equals 0. And we're specifically going to be looking for solutions centered at 0. And that's going to be a common thing. We're not really going to branch out away from solutions centered at 0 with this batch of material. So that's a fairly safe thing to say. So we can look at this and we can say, well, there are no singular points for this differential equation. So that means that there must be two power series solutions that are going to converge for all values of x. So the first thing we're going to do is we're going to say, well, what if there is a power series solution? It would look like y equals the sum from n equals 0 to infinity of c sub n times x to the n for some c sub n value, right? If we have this power series solution, then when we plug it into our differential equation, it must make the equation true. So we want to plug it in. So in order to do that, we're going to need to take the second derivative. So the first derivative, I start my sum at 1 instead of 0, and we have c sub n times n times x to the n minus 1 as our first derivative. Then we take our second derivative by taking the derivative of our first derivative. This time my sum will start at 2 up to infinity, and we'll have c sub n times n minus 1 times x to the n minus 2. So just a really quick recap. We're going to suppose that y equals the sum from n equals 0 to infinity of c sub n times x to the n is a solution of our differential equation. And then we're going to take the derivatives that we need for our equation. Our second step is going to be plugging them in. So let's do the substitution. So y double prime substituted in, we're going to put in n equals 2 to infinity, that sum of c sub n times n minus 1 times x to the n minus 2. We're going to subtract from that x times y, and we're substituting in for y, n equals 0 to infinity of c sub n x to the n, and it's all going to equal 0. Now notice I'm in a situation where I have sums, I have power series that are being combined through subtraction, which is totally legal, except my indices don't match up for me to be able to put the sum together. So we need to shift summation indices in order to be able to combine them. So our third step is going to be shifting those indices and combining them. Now remember, to shift the indices, it's helpful for us to write out some terms of the sum. So let's do that. For my first sum, I get c sub 2 times 2 minus 1, or times 1, times x to the 2 minus 2, or x to the 0. Then, plugging in n equals 3, I get c sub 3 times 3 times 2 times x to the first, plus, plugging in 4, I get c sub 4 times 3 times x squared, and it keeps on going. And now for my second sum, I'm actually going to multiply by the x there too. So if I plug in n equals 0, I'm going to get c sub 0 times x to the 0 times x. So that's really going to be c sub 0 times x to the first, plus, and now plugging in n equals 1, I'll get c sub 1 x to the first times x, so x squared. And then I'll get c sub 2 x squared times x, so x cubed, and so on. And remember, I want to be subtracting my second sum from the first. So taking a look and matching up where my exponents are the same on x, I have an extra x to the 0 term in my first power series, my first sum. So I'm going to write that one out separate. So I'll get c sub 2 times 1 times x to the 0, so times 1. So times 2, so I'll have 2 c sub 2 plus, and now everything has an x to the first power. So I'm going to be taking a sum. It makes sense to start at some k equals 1 value, since that's the power on x. And I'll of course be going to infinity since it's a power series. And I'm going to rewrite what's going on here in terms of k equals 1. So c sub 3, to get from 1 to 3, I need to add 2. So I'm going to have k plus 2 times 3 times 2. Well, 3 to get from 1 to 3 again is k plus 2. To get to 2 is k plus 1. And then we have x to the k. Then we're subtracting from that c sub 0, so that's c sub k minus 1 times x to the first, or x to the k. And then this is going to equal 0 because this is a new way of writing my differential equation. Now I'm going to factor out an x to the k just to make our lives a little bit easier. And so we're going to end up with 2c sub 2 plus the sum from k equals 1 to infinity of k plus 2 times k plus 1 times c sub k plus 2 minus c sub k minus 1 all times x to the k is going to equal 0. Now that we've shifted indices and combined successfully, we're ready to complete our next step. Our next step is going to be to invoke or use the identity property. Now remember, the identity property says if you have a power series that equals 0, then c sub n is going to equal 0 for all n. So what that means for us is that k plus 2 times k plus 1 times c sub k plus 2 minus c sub k minus 1 is going to equal 0 for all k. So k can equal 1, 2, 3, and so on. And it always has to equal 0. That means the coefficient on our x term always has to equal 0. Also, we can see that 2c sub 2 also needs to equal 0 since it's being added to this power series, and the power series got to be 0. It's part of the power series, you know? So 2c sub 2 equals 0. Well, that means that c sub 2 is going to equal 0. And that's kind of a starting point for us. If c sub 2 is 0, then we could maybe find the next c values above it. So let's take a look at what's happening here again. So we have k plus 2 times k plus 1 times c sub k plus 2 minus c sub k minus 1. So k plus 2, if we put in values of k that are greater than or equal to 1, it's not going to be equal to 0. So k plus 2 is not equal to 0. Also, if I put in values of k greater than or equal to 1, k plus 1 is also not equal to 0. So I know that the quantity k plus 2 times the quantity k plus 1 is not going to equal 0, combining those two. So since I know that k plus 2 times k plus 1 is not equal to 0, that means it's fair game to divide by it, which means I can solve for c sub k plus 2. I can do that by adding c sub k minus 1 to the other side of the equal sign, and then dividing by the quantity k plus 2 times the quantity k plus 1. And again, k can still be 1, 2, 3, and so on. So let's take a look at what happens when we plug in some of these values of k. So let's plug in the value k equals 1. Then I'll have c sub 3, so 1 plus 2 is 3, is going to equal c sub 0 divided by 1 plus 2, so 3, times 2, or c sub 0 over 6. If I plug in k equals 2, I'm going to get c4 equals c1 divided by 4 times 3, or c1 divided by 12. Plugging in k equals 3, I get c5 equals c2 divided by 5 times 4. Now, since C2 equals 0, this is going to be 0 over 20, or just 0. Plugging in k equals 4, I get C6 is going to equal C3 divided by 6 times 5. Now remember, C3 is actually equal to C0 divided by 6, so this is really C0 over 6 times 6 times 5, or C0 divided by 180. Plugging in k equals 5, I have C7 equals C4 divided by 7 times 6. Well, C4 was C1 over 12, so this is C1 over 12 times 7 times 6, or C1 divided by 504. Plugging in k equals 6, I get C8 equals C5 divided by 8 times 7. Now C5 was 0, so that means that this is 0 over 56, or 0. And we could keep on going with this, and this pattern that's emerging would continue. So we would have a C0 term, followed by a C1 term, followed by a 0. Over and over and over again. So once we've gotten to the point where we kind of see the pattern that's happening, we're ready for step 5. Namely, substitute the coefficients in. So what do I mean by that? Well, we originally said that the solution to this thing was going to be some power series, y equals the sum from n equals 0 to infinity of c sub n times x to the n. So I already know what some of these values are. So plugging in 0, I have c sub 0, x to the 0, so 1. So I've just c sub 0. I don't know anything about c sub 0, so I leave it that way. Then plugging 1 in, I have c sub 1, x to the first. Plugging 2 in, I have c sub 2, x squared. Then I have c3, x cubed, c4, x to the fourth, c5, x to the fifth, and I could keep on going. But I'm going to stop there instead and say, all right, well, we know that c3 actually is c0 divided by 6, right? So let's plug it in. So making these, substituting our coefficients that we know in, I have c sub 0 plus c sub 1 x plus c sub 2 I know is 0 plus c sub 3 I know is c0 divided by 6 x cubed plus c4 I know is c1 divided by 12 x to the fourth. C5 I know is 0. C6 I know is c sub 0 divided by 180 x to the sixth. C7 I know is c1. C7 I know is c1 divided by 504 times x to the seventh, plus I know c8 is 0, plus, and I can continue this pattern on forever and ever and ever. So after we've done this substitution, we can notice that we have terms that go with C0s, and we have terms that go with C1s. Everything else is zeroed out. So our next step is going to be to group the C1 terms together and the C0 terms together. So if we do that, then we end up with that y that we had is really equal to some function times c0. So c0 times maybe y1 of x, and c1 times some other function of x, maybe y2 of x. And we can even write these out. So we know that y1 of x equals all of our c0 terms. So it's going to equal 1 plus x cubed over 6 plus x to the 6th over 180, and so on. And we know that y2, the things with the c1s, look like x plus x to the 4th over 12 plus x to the 7th over 504, and so on. So these are actually power series, and we can write them as power series. So with my first one, I have 1 as my first term, and there's no x with it, so I'm going to leave it outside since there's no x with it. And then I'm going to start my sum with k equals 1 up to infinity. And what this is x to the 3 times k, or 3k, divided by, and it's actually 2 times 3 times all of the values up to 3k minus 1 times 3k itself. So we can check that and make sure it works for our first term. Well, 3k minus 1 is going to be 2. 3k is going to be 3, so it'll just be 2 times 3. For our second term, 3k minus 1 will be 5. And 3k itself will be 6. So we'll have 2 times 3 times 4 times 5 times 6, which is 180. So that works. And then for y2, we can also write it as a power series. So again, just so I get to start my sums both with a k equals 1, I'm going to keep the x out in front. It also doesn't fit quite the same denominator pattern as everything else without some finessing. So it's easier to describe the power series if we pull the x out and let everything with the denominator be inside our power series. So again, we'll start our sum at 1 up to infinity. This time in our numerator, we have x. It's raised to the 4th power, which we might be tempted to say is 4k, but they're going in multiples of 3. So what's really happening is we're doing 3k plus 1 as our exponent. And then our denominator is actually 3 times 4 times everything up to 3k times 3k plus 1. And again, we can check that and make sure it works. For our first term, we're good. For our second term, our exponent ends up being 7, which is right. And we end up going up to 6 times 7, so 3 times 4 times 5 times 6 times 7, which is 504, so we're good. So what we've just done here is y1 is a solution to our differential equation, and it's a power series. y2 is a solution to our power series, to our differential equation, and it's a power series. And y equals c0 times y sub 1 plus c1 times y sub 2 is the general solution to our differential equation.